Hey, Mr. Allred, and we are doing rational functions. We're finding some characteristics so we can graph them. We've done vertical asymptotes, and now we're going to move to horizontal asymptotes. Horizontal asymptote occurs when the function value, that's the output, approaches a specific number as you move infinitely away from the origin. So that means you're moving toward the x values of infinity or positive or negative infinity. So that would be over here or over here. You're moving toward the ends of the graph. And it says that the outputs go toward a specific number. So let's see here. I've got the example here just to kind of lay it out here. The function f of x equals the numerator 4x minus 3 over denominator x plus 5. So in this case, what I did was I took x values starting at 0, where the origin is, and just for an example, I ran them all the way up to what looks like 100,000. And as we make the x input larger, what we see on the outputs, it starts at negative 0.6, and then it starts to increase a little bit. By the time the input becomes 100, we're at about an output of 3.8. And 1,000, 3.97, 10,000, 3.99, 100,000, 3.999. So that is going towards 4. Now, technically, it'll never really be 4 because the thing that would make it 4 is really undefined. So in this case, we're not going to get to 4. We're just going to get closer and closer to it. So if we make the input 1,000,000, it might be an output of 3.99997 something. But what this does is it creates a horizontal asymptote, a horizontal line, that our graph will get closer to as we move away from the origin. And horizontal lines look like y equals, in this case, 4. And we'll see where that comes from in a second. My graph is not the best, but just to kind of make sure you can see it, I wanted to make sure you could see that it kind of flattened out and got close to 4 as it went out. In which case I had to zoom out so much so it's kind of hard to see the numbers. That should be a flat line going across y equals 4. But as I move extremely to the right and extremely to the left, the graph flattens out there. So let's talk about where these come from or how to do them without having to make this big old table here. So here's the rules for horizontal asymptotes. We're going to have a rational function, which means there's going to be some type of polynomial in the numerator, some type of polynomial in the denominator. So what I've got here is I've listed the largest degree of the top and bottom from that polynomial, and I've called it x to the m on top and x to the n on bottom, and each one of those could have a coefficient. And since they're the largest, what we're just going to kind of do is discount everything after them. So we're really dictated by the largest exponent on top and bottom. So I have it written as a times x to the m on top, and then there could be some other stuff after it, but all the exponents have to be smaller than m. And then on the bottom, b times x to the n plus some other stuff, but all the other exponents beyond there have to be smaller than n. So m is the largest exponent on top, n is the largest exponent on the bottom. And we've got 3 rules here. If the top exponent is bigger than the bottom, there's no horizontal asymptote. And the reason for this is basically those exponents are determining which is going to be bigger, the numerator or the denominator. And if the top exponent is bigger than the bottom, then the top grows faster than the bottom, so the numbers just keep getting larger and larger and larger that come out, so it never flattens out. Okay. So in that case, what we're saying is the outputs keep getting larger, and it doesn't flatten out to like that horizontal line. If m is less than n, so that means the bottom's getting bigger quicker. Okay, and if that's the case, if we make bigger and bigger denominators while the top doesn't really change that much, then we get our fraction closer to 0, kind of like 1/2, 1/3, 1/4. We make the bottom bigger while the top doesn't really change. If that's the case, the horizontal asymptote is y equals 0 because that's what the fraction is getting closer to. And then if it's not greater than or less than, then it must be equal to. So there's only three choices here. So if x to the m and x to the n have the same exponent, basically we could almost kind of cancel them out, and that would leave the a over b, the coefficients. So the horizontal asymptote goes to y equals a over b. Okay. Now, one thing that should be mentioned here, with the vertical asymptotes, we could have more than one. But with the horizontal asymptotes, there cannot be more than one. Okay. There doesn't even have to be one, since we already see that there's a case here where there's no horizontal asymptote, but there cannot be more than one. If it had more than one, it wouldn't be a function. So let's revisit some of the functions we've already worked with. So now we're going to find the horizontal asymptote for the function 3x squared plus 2 over x squared minus 5x minus 6. We've already done the vertical asymptotes, and I have them on the graph. X equals -1, y equals 6. But let's look at this. So we're going to compare the largest exponent on top with the largest exponent on the bottom. So in this case, if we're trying to make a statement, we could say that m equals 2 from the top, n equals 2 on the bottom. So m equals n. So in this case, we could say that the horizontal asymptote would be a over b. Well, what's a? A is this number, 3, the coefficient up top, and the b, you don't see it, but it must be 1. So the horizontal asymptote is going to be y equals 3 over 1 or 3. So I'm going to put that on my graph, a horizontal line across here. Okay. So the top and bottom exponents were the same. So that meant that we looked at the coefficients. Okay, and that was, from the set of rules I had, that was the third one. Okay. The next example, 5x plus 2 over x squared minus 36. When we did this one earlier, we had the vertical asymptotes x equals -6, x equals 6, which I already have on the graph. But now we're going to compare the exponents. Up top, we don't see an exponent. On the bottom, we see a 2. That exponent we don't see up top must be a 1. So in that case, m equals 1 and n equals 2, so m is less than n. Let me clean that m up a little bit. So if that's the case, we said if the bottom is bigger than the top, then there is a horizontal asymptote at y equals 0. So that was, let's go back. That was the second rule, m less than n. Okay. So that means there's going to be a horizontal asymptote on the x-axis. So let's highlight it really good so we can see it. Okay. The next one here, we have x cubed plus 3x minus 4 over the denominator x minus 5, and we already established a vertical asymptote at x equals 5. But on this one, the numerator has an exponent of 3. The denominator, you don't see an exponent, so it must be 1. So in this case, m equals 3, n equals 1. Got a little messy. The top exponent is 3, the bottom exponent is 1, so m is greater than n. So that means there's no horizontal asymptote. So when I say a horizontal asymptote, there is none. Okay. So that means it doesn't flatten out as we go way out there. Okay, and that was the first rule. The last example I have here. 3x squared plus 2x minus 4, and that's all over x plus 2. We already established a vertical asymptote at x minus 2. So once again, The exponent up top is a 2. The exponent at the bottom, we don't see it, so it must be a 1. M equals 2. N equals 1. M is greater than N, so that is no horizontal asymptote. Okay. Alright, so that's horizontal asymptotes, and we're going to pick back up and keep working with our graphs in a little bit.